To practice using Lagrange's equations, we will look at another system with 2 degrees of freedom, a pair of masses on springs. Recall the process of using Lagrange's equations. Firstly, we decide how many independent coordinates or generalised coordinates are needed and choose appropriate ones. This enables us to write down energy, power and work terms as needed. The difference of kinetic and potential energy is the Lagrangian L. Derivatives of L and derivatives of power dissipated and work done by external forces with respect to a particular coordinate allow an equation of motion to be written for that coordinate. We will continue writing equations for all coordinates. The classic 2 degree of freedom problem is a pair of masses oscillating on springs. This can represent quite a lot of physical situations, such as a portion of a vehicle bouncing on a wheel, which in turn bounces on the road. In the mass spring system, first let's use the relative deflection of the top spring as a coordinate. This makes coupling terms appear in the kinetic energy and hence in the mass times acceleration terms, but removes coupling of the stiffness terms. We will ignore gravity as it just causes static deflections. To estimate natural frequencies, we can leave out the dampers as they complicate this task and may only make a small difference in the values. Hence, let's just write down the kinetic energy and the potential energy to obtain undamped free vibration equations. So to use Lagrangian mechanics on this, we need to write down the Lagrangian, which in this case is to do with the kinetic energy of both these masses. That's a half m1 x1 dot squared for mass 1 plus the kinetic energy of mass 2. Now we have the motion of mass 2 is x1 plus xrel. We have to add on the relative motion to mass 1. So the kinetic energy will depend on the velocity of mass 1, x1 dot, plus the relative velocity, xrel dot, to give the velocity of mass 2, and that is what we square. Now, I've got to subtract the elastic potential energy, which is minus a half k1 x1 squared, and that of the second spring is also fairly simple because the deflection of the second spring is this relative deflection xrel. So it's minus a half k2 xrel squared. We can differentiate this expression for L with respect to x1 or with respect to xrel to give our 2 equations of motion. Now let's start with x1. And the first term in Lagrange's equations is d to t of the L to x1 dot, and that'll just give us from the first kinetic energy term, we'll get m1 x1 dot differentiating with respect to velocity, but we also have to differentiate with respect to time, so it becomes double dot. The second term there, we've got an expression in brackets, so we differentiating that, a half m2 expression in brackets squared just becomes m2 times expression in brackets except we also have to differentiate with respect to time, so once again we get double dots. Now the other term there of course is we've got to find the L to x1, and that's relatively simple because it's just minus k1 x1 from the third term in L. So what happens if we put those two together? What we get is we've got 2 mass terms multiplying x1 double dot, so we can group those together. It's m1 and m2. It's m1 plus m2 x1 double dot and m2 x relative double dot, and then it's minus del to x1, which is plus k1 x1 equals 0. And that's our first equation of motion for undamped free vibration. Now if we do the same thing for x rel, it's d to t, to L, to x rel dot, what do we get this time? Well, this time we only need to look at the second kinetic energy term. So it's just m2 x1 dot plus x relative dot, but differentiated with respect to time becomes double dot. And the L, the x relative, that just picks up the energy stored in the second spring, which is K2 x rel. So if we put those together, we get a second equation of motion. And this time, well, once again, let's put x rel first because it's the one we're talking about for this equation. But there's a coupling term, you see, to x1 in the inertia. And minus the L to x rel is plus K2 x rel equals 0. And that's our second equation of motion for free vibration. Note they both have coupling terms in the mass, but the stiffness terms are not coupled. And that's a result of our choice in coordinates. Now let's do the problem again, but this time using the total motion of the top mass x2 as the unknown. This decouples the kinetic energy and hence the mass times acceleration terms. The coupling now reappears in the stiffness terms as the deflection of the top spring now depends on a difference in coordinates. So to write down L again with our change in coordinates, kinetic energy is now simpler because it's a half m1 x1 dot squared plus 1/2 m2 x2 dot squared. The potential energy for spring 1 is the same, it's just a half k1 x1 squared because x1 is the deflection of spring 1. But spring 2, I've now got a difference in deflections describing its energy, which I could write as x2 minus x1 or x1 minus x2. It doesn't really matter because it gets squared. So now we can differentiate with respect to either x1 or x2. Starting with x1, we take d to t to L x1 dot. And this time it's obvious we just get the first mass there as the mass times acceleration. If I take the L, the x1, this is a bit more complicated because it involves both springs. It's going to be minus k1 x1. And the second one is, well, once again, it's going to be k2 x2 minus x1, but I've also got to differentiate with respect to the contents of the bracket, and there's a minus sign in front of x1, so it's multiplied by minus 1. And we could tidy that up a bit. Group together the terms in x1. It's minus k1 plus k2. And the term in x2, I've got two minus signs there cancelling. That's going to come out positive. It's k2 x2. So we put those two together to get our equation of motion. That's going to be m1 x1 double dot, and I have to subtract the L to x1, so that now becomes plus k1 plus k2 x1 minus k2 x2 equals 0. Note again that the term in x1, the stiffness term, is positive. So therefore this does describe an oscillation. Now, second coordinate use x2, derivative with respect to x2 dot, we'll pick up the second mass only, so that's it's just m2 x2 double dot, and the derivative just with respect to x2 is a bit simpler this time because we're only looking at the second spring. And if we just differentiate it, it'll be minus k2 x2 minus x1. You check what's inside the bracket, but this time it's just a plus 1 in front of the x2, so there's nothing else going on. So therefore we can put those together and write down our equation of motion. And it'll be m2 x2 double dot minus the L to x2, so now plus k2 x2 minus k2 x1 equals 0. Note again here the term in x2, the k2 x2 is positive. We have an equation for oscillation. Also note that the coupling terms and the stiffness are both the same, really, aren't they? The first equation's got minus k2 x2. The second equation's got minus k2 x1. In this video, we have demonstrated the use of Lagrange's equations to obtain undamped free vibration equations for a system of two masses on springs. We have demonstrated that even for this simple case, there are choices in the coordinates that we can use.